Hi everyone, thanks for attending this talk. My name is Emmanuel Dufour. I'm with the African Institute for Mathematical Sciences in Muizenberg, Cape Town, South Africa, and with Stellenbosch University. And this talk is titled A Survey on Factors Affecting Facial Expression Recognition based on Convolutional Neural Networks. And thanks to the NRF and AIM South Africa for supporting this work. So just a quick overview of the talk. I'll start with an introduction to facial expression recognition, and then I will discuss the various steps to consider when implementing a convolutional neural network, or CNN, for expression recognition. And the purpose of this talk, so this isn't a technical talk, it's more about providing a roadmap to students and researchers, so new honors students, new master's students, new PhDs who are interested in this field, and to provide them with a roadmap to just help accelerate their research and to spend more time investigating new things as opposed to figuring out how to get started. So what is facial expression recognition? Well, humans convey their emotions across in various forms, and one of which is expressed through changes in a person's face as a consequence of their emotional state. So facial expression recognition is the ability to recognize the expressions being conveyed through these changes in the face. And Paul Ekman proposed that there are 6 classes, namely happiness, sadness, anger, surprise, disgust, fear, and also just the neutral class. So what is automatic facial expression recognition? Well, in this case, we have some input images. So here are some examples of 3 input images, and then we would pass it through to some algorithm. And then the algorithm would then return the expression for each of the images, which is the output in this case. So here's an example of Microsoft's Emotion API, and you can give it an image. So this is an API, but you can also play with this online. So you can go online and try it for yourself. So you can give it an input image, and then you would send it through to the API server and get a JSON response back containing all of the different scores for the various possible emotions. So let's take a look at some applications. So here's a paper that focuses on pain detection, and the authors state that pain is usually expressed through self-report verbally. So the abstract reads, if the patient is a child or has limited ability to communicate, mentally impaired, or patients having assisted breathing, self-report may not be a viable measure of pain. Here's another study, and the focus here is on empathetic robots. So here the abstract reads, they mention that a social robot would be able to encourage a cancer patient to take their medication in a more efficient manner if they could understand the emotional state of the patient. And here's another application in e-learning, and here in this study the authors proposed to use automatic emotion recognition in a setting where students are learning remotely from the educator. And other applications include monitoring stress during driving, for example, or market research, trying to understand how people react to a particular new product. This is traditionally quite labor-intensive, and, for example, call centers where you want to monitor the emotional state of the agents at the call centers as a performance metric. So let's have a very quick recap on convolutional neural networks and classification. So here on the left we have a picture of a bird, and we would apply these convolutions, which creates a feature map that contains various layers, and we would apply some nonlinear activation functions. So for example, the ReLU activation function. And then we would apply max pooling, which kind of compresses the feature space. Eventually, at some point, we create a long vector, and then we apply a number of fully connected layers, and then we would have the number of units at the end corresponding to the number of classes in the particular data set. And the idea with convolutional neural networks is that given some image, the CNN is able to learn how to abstract. So initially it learns simple edges, and then it learns how to combine those simple edges into something more complicated. And then the next layers take the previous layer, which has slightly more complicated combinations of edges, and create something more complicated, until eventually it has a very good visual representation of the classification task, for example. So how do we go about making a CNN for facial expression recognition? Well, we've surveyed 100 plus articles over the last recent years, and each of the major steps in this talk will be discussed. So the primary aspects of implementing a CNN for emotion recognition will be discussed. And I'll refer to these as steps. I'll say step 1, this is what you should do. Step 2, this is what you should do, and so on and so forth. So the first step is to actually just get a data set. And there's a lot of data sets available. So for example, CK+, Jaffe, FIR 2013. So there's a lot of them available. And how do you select which data set you're going to use? And each data set has different end user agreements that you have to sometimes sign to. So let's take a look at the ones that were used the most commonly in the studies we looked at. So here we're looking at the different types of characteristics. So some of them are posed. Some of them are not posed. So posed is when they're in the lab and someone comes and they're asked to pose the emotions. Not posed means it's typically a real emotion. So it's not, you're not asked to pose the emotion. So pictures from the internet. And gender and age are also important to consider. So some data sets have a large age group, and some data sets are more restricted, and some data sets have a equal gender balance, and some of them are more biased towards a particular gender. So here's an example of a spontaneous versus a lab image. So on the left, this is a spontaneous image, someone expressing emotions, and on the right, this is typically the same emotion, but someone, an actor, for example, or someone who's rehearsed the expression, they're asked to pose in front of the camera. So I don't know about you, but for me personally, the image on the left is far more realistic of someone expressing that emotion of what I would probably see in the real world, as opposed to the image on the right. And there are some other limitations with using data sets that have posed pictures. So for example, the lighting conditions are typically fantastic. They use high quality cameras and high quality flashes from various angles. So the lighting, the distribution of light across the face is usually very good. And of course, unrealistic poses, and sometimes they're asked to rehearse. So they actually hire amateur actors, and they ask them to rehearse the expressions in advance. So not very realistic. So let's take a step back and ask ourselves, what actually makes facial expression recognition challenging? Well, it's a combination of things, such as does the person have a beard, a mustache? Are they wearing glasses? What about the ethnic differences? What about the difference in age and the head pose? So there's a lot of factors that actually make it challenging. And so here's an example. So do you think that a neural network trained will be affected if it's trained on the image on young people smiling? So here you can see the these two edges near the person's mouth, and those appear when they're smiling. But here's a picture on the right of someone who's slightly older, and they're not smiling, but they have those same folds. So, you know, age, gender, and all of these things play an important role. So we shouldn't use data sets that are more skewed towards one end than another. So my recommendation here is to use data sets such as the CK+, Jaffe, and FIR 2013 just as a benchmark to check that your neural network is doing a good job. Kind of as someone would use MNIST to just check that everything's working. But then don't go ahead and report on that too much. rather try and use in the wild data sets that are far more realistic for benchmarking purposes, and also to consider compound expressions, which is a combination such as happily surprised or angrily disgusted. So these combinations make it more realistic and more interesting. And what if you wanted to build your own data set and scrape online pictures? Well, there are studies that use between 6 to 1,000 keywords, and then they go and they download images and create their own data set. And there's some other factors to consider, such as academic licensing. Some data sets have very strict licenses when you download them, and some of them less strict. So these are just some things to consider when downloading data. Okay, so step 2 is to pre-process the dataset, and here the goal is to try and assist the CNN by performing some transformations. So here, the 2 images on the left, the distribution of light isn't that great, and on the right, we can apply some techniques, for example, histogram equalization, and then we have a better light distribution across the face. So we really just want to try and assist the CNN by pre-processing and dealing with light, for example. Another thing we might want to do is to have some face detection, and we can then crop faces, detect landmarks to fix orientation and align the pictures, and also just to focus on extracting certain features from the face. For cropping, first we will need to actually detect the landmarks, and then we can crop useful facial features and remove additional noise in the relevant regions, such as the hair, for example, or the clothes and the background. Those are things that don't help us for expression recognition. And here, from the studies surveyed, Violo-Jones was the most frequently used method, and this was implemented using dlib and OpenCV, and I saw some authors using Google Vision API. In terms of image enhancement, the posed datasets don't really have that much of a problem because the lighting conditions are usually great in the posed datasets. So this is typically a problem in the wild datasets. And from the studies surveyed, histogram equalization was used most frequently. So here you can see on the left, we have before and after histogram equalization, and some other authors tried an ensemble of various techniques, and that also worked quite well. So my recommendation here is to definitely align the faces, so detect the landmarks and try and align the faces, and then you can use Violo-Jones for that. And a lot of studies show the effects of not doing pre-processing and doing pre-processing, and they tend to show that pre-processing actually does help increase the performance. So I definitely encourage you to go ahead and implement it, and to use histogram equalization to deal with lighting problems, and that tends to work well. And you don't actually have to input RGB images into the CNN. You can just use grayscale, and one of the good things about doing that is it actually just reduces the number of parameters in the neural network, since your first layer just has 1 channel as opposed to 3 color channels. Okay, so step 3 is to augment the dataset. So once you've acquired the dataset and done some pre-processing, you want to try and increase the number of examples. So for example, the CK Plus dataset only has less than 600 images, and the Jaffe dataset has less than 300 images. And we know that CNNs work best with a large amount of images. So we can apply these augmentation techniques to increase the amount of data that we have. And the commonly used techniques was horizontal flipping, rotation, cropping, and zooming. So horizontal flipping is the easiest one to implement, and it basically doubles the amount of data that you have. Rotation was implemented quite a lot, but it requires a decision to be made on the angle that you're going to use. And typically this was done both from the clockwise and anti-clockwise direction, but one has to ask themselves, what angle do you use? And my advice here would be minus 10 to 10 degrees, for example. Cropping was used quite a lot, and the nice thing with cropping is we can actually augment the dataset quite a lot. So we can crop the top left, top right, bottom left and bottom right and the center. And now we've gone from one picture and now we have 5 additional pictures. So that actually augments the data set quite a lot. In terms of literature, there wasn't a lot of consistency on the approaches used here. So the recommendation is to use it, but there's no real guidance as to what is the best approach. So here, once again, some studies have shown the effects of not using it and using it, and all of them illustrate that you should definitely use it. It increases the performance of the CNNs. At the very least, use horizontal flipping to augment the data set by 2. And in terms of software, you can use OpenCV, and you can also augment your data set by collecting additional images, by doing keyword searches on internet searches. Okay, so now the next step, we can make a few decisions. We can train a CNN from scratch. We can use transfer learning to avoid training from scratch, or we could train an ensemble of CNNs. And let's talk about transfer learning. And so here the idea is that a CNN trained on one problem can be applied to another. And the rationale being that it takes a lot of time, especially on limited hardware. So why don't we take advantage of transfer learning and not have to train from scratch? In terms of evaluation, not a lot of studies have done fair evaluations. So here the recommended approach is to have a subject-independent evaluation where the subject does not appear in both training and testing data sets. And a lot of studies just use a single data set, and that's not sufficiently representative of the CNN's ability to generalize. So I definitely would recommend using a few data sets. And the cross-database approach is when you train on datasets A and B, for example, and then you evaluate it on datasets C and D. So datasets C and D are never seen during training, and that's quite a fair evaluation. In terms of software, Keras and TensorFlow were used most frequently. So there are a lot of open questions and things that could be investigated, and I've listed a few. And I'm just going to touch on the last one because that one is very interesting. There was a study that tried to change the feature space of the input. So instead of using RGB input or grayscale input, they tried to transform the RGB input into a new input feature space. And you can get more details from the paper, but it turns out that that transformation from RGB to a different space led to an improvement of results. So to conclude, it's quite easy. So well, easy, of course, is a relative word here, but given these steps and given the details that I present in the paper, it's relatively easy for someone to boost their work as opposed to trying to figure out. So if you follow the recommendations, you can kickstart this research quite quickly. And this is a very active area of research. A lot of work has been done since 2017. So, what's next? And given that we're in Africa and we have limited hardware, I'm interested in knowing, how accurate can we build these automatic facial expression models, for example, on a Raspberry Pi that has a very limited hardware. And if you wanted the full documented evaluation or survey on this, I have a 53-page split into 2 chapters, and I provide the link at the bottom. So thank you for attending this, and I'm open for questions, and you can reach out to me on this email address. Thank you.